So we're going to try to see if we can understand the theory behind all of these four mechanisms. They are all relatively similar, so let's see how we can work it out so one will favor the other. The first thing we gotta know is that Sn1 and E1 are always in competition. Also, Sn2 and E2 are always in competition. You can check out my website and you will see mechanism and examples for each one. So I will not really get into the mechanism part of it. I will try to go with the analysis of it. So there are several things we have to pay attention to when we're looking at this. So the basic three things that I mentioned in the videos are substrate, also the nucleophile, the leaving group, and we will introduce the medium. So we have those four things. Let's try to start with the leaving group. So the leaving group. You gotta remember that you have your leaving group X, I will say X, with your chain of carbons, and then you have your nucleophile. And as the product, you will get the nucleophile right here without the minus, and for the elimination is different, but we'll focus on that. So if your leaving group is a tertiary, for example a tertiary halide, you can imagine that when it leaves, it makes a pretty decent carbocation. It makes a tertiary carbocation. It's pretty stable. So that leaving group is going to leave. So if we say leaving group tertiary, it's going to favor Sn1 and E1 because those are carbocation intermediates. While if it's something like this, it's a primary, then this will not make the primary carbocation. This X is not going to leave because the molecule is going to be extremely unstable. So instead, the nucleophile is going to do a backside attack because the other groups are pretty small, and this one's going to leave, as it happens in Sn2 and E2. So primary, we're talking about leaving group right now. So primary is going to favor Sn2 and E2. Now, the problem comes when we're talking about a secondary leaving group, because a secondary leaving group can make a relatively stable carbocation, so you will have Sn1 and E1, but it also has plenty of room for a backside attack, so you will have Sn2 and E2. Okay, let's try to analyze now substrate. So pretty much the substrate is the molecule we're working on, and we're going to go pretty much under the same principle as we went on leaving group. You have bulky and you have non-bulky. So a bulky substrate would be something like, let's say, that's pretty bulky. Something not bulky would be, again, CH3Br. So obviously, in a substrate this big, you do not have access to the backside of this carbon. Too many electrons floating around, so the nucleophile is not going to have any entrance to make it there. Thus, we say that it favors E1 and Sn1. So we say bulky, and we're talking about substrate, it will favor Sn1 and E1, and not bulky. It will favor the E2 and Sn2. So that is for substrate. Now, the next one we're going to check is nucleophile. Now, we have two types of nucleophile. We have weak and we have strong nucleophile. So E1, Sn1, E2, and Sn2. So we said that for nucleophile you have weak and you have strong. Now, what this will do, the nucleophilicity is going to give you the difference between if it undergoes elimination or if it undergoes substitution. It's not going to go so much on which number it goes. For example, if you have a strong nucleophile, let's say an H2, that is more likely to pull the proton to make it go elimination than to act as a nucleophile and do a backside attack or just do a substitution. So pretty much the stronger the base, the more you're favoring the eliminations, the E1 and E2. The way you figure out how basic is your nucleophile is if you have your periodic table right here, then the trend is going to go this way and it's going to go up. So for example, if you have NH2 and you have OH minus, and you have to rank them, which one is more basic, then you have your O right here and you have your N right here. So by the periodic trend, you say, okay, this one is a better base. Thus, this one will favor both eliminations, while OH is going to be better at substitution than NH2. So pretty much we're saying that the nucleophile makes the distinction between E1 and Sn1, and it makes the distinction between if it undergoes E2 or it undergoes Sn2. Now, you can also have bulky bases, and that you pretty much already know, okay, if it's bulky, then you know what, it's not going to be backside. It's going to allow the substrate to work by itself. It's going to make a carbocation, or so on and so forth. Okay, the last thing we need to consider is the medium you're making a reaction in. So for mediums, you have polar product, you have polar aproduct, you have nonpolar aproduct. So pretty much what this is telling you, if you remember your general chemistry, is polar. If it's polar, then you have a polarized side, a negative side, and you have a polarized side, positive side, kind of like the Earth. You have a North Pole and a South Pole. And the product, it tells you that it can donate protons. So a good example would be water. H2O, you have your oxygen, which is highly electronegative. You have your hydrogen, and this goes that way. The dipole moment goes that way. So this is a polar molecule, and these hydrogens can be pulled as protons. So you have your polar product, you have your polar aproduct, which it is a polar medium, but you do not have any hydrogens to donate. A good example would be acetone. So you have CH3, C double bond O, and CH3. This oxygen is makes it polarized, the whole molecule, but you do not have any H's attached to it. This bonds right here with the carbon are non-polar, so you cannot. These are not protons to donate. So pretty much it's polar non-product or a product. And then you have non-polar, which could be something like CH2, Cl2, which is non-polar and it's a product. So you do not have any H's to donate anyway. So how does this relate to our combination of reactions? Well, the way it happens is if you have a nucleophile, if you have a strong nucleophile, and you put it in a polar product medium, so let's say plus H2O, the one we picked, then what's going to happen is instead of the nucleophile going to your substrate, your nucleophile is going to come to one of the H's right here and it's going to get spoiled. You will have your nucleophile plus an H and your reaction is not going to go. If you have a weak nucleophile, then it's going to be harder to pick up that H. So you will have some of the nucleophile react with your substrate. Now, if you have a polar A product, then you can use a strong base, nucleophile, plus let's pick acetone. Then this will be a really good medium and a good base to make an elimination reaction, because you are not spoiling your nucleophile and your nucleophile is going to act as a base. So you are definitely trying to undergo elimination. When you have a weak nucleophile and you have a polar A product, then the outcome is going to be the same. Now, non-polar A product, pretty much you do not, your nucleophile doesn't pick up the H. There's no H to pick up, so you are not spoiling the nucleophile. Pretty much you have to think, am I spoiling the nucleophile or not? So A product tells you you are not. Product tells you yes. Now, in what cases do we want to spoil the nucleophile? For example, if we want the formation of a carbocation, then you do not want a really aggressive nucleophile, because then it's just going to do a backside attack, or it's going to pick that proton. You want it to wait, pretty much to wait until the carbocation forms. So you do want to spoil the nucleophile. You do want to make it wait, and the way you do it is with the medium. Okay, let's recap really quick. We have substrate, nucleophile, leaving group, medium, and nucleophile. This is the way I broke it down. So pretty much the substrate will group it into either E1 Sn1 or E2 Sn2. Your nucleophile, either if it's weak or strong, will favor the eliminations or the substitutions. Your leaving group, depending on the degree, will be either 1 or 2. The medium, since it affects the nucleophile, then it can break it down into each one. And your nucleophile, the bulkiness of it, it can make it undergo the 1s or the 2s.